Okay, so I'm going to talk about fusible numbers and Peano Arithmetic, and this is joint work with Jeff Erickson and Junyang Xu. And at the end, I'll present some more recent work with Fedor Pahomov and Sasha Buffetova. So let's take a look at this strange recursive algorithm. So this algorithm M of x, when given x, if x is smaller than 0, it returns minus x. Otherwise, it returns m of x minus m of x minus 1 divided by 2, making two recursive calls. So, for example, m of 1 makes this calculation, and at the end, it returns 1 over 8. M of 1.5 returns 1 over 32. M of 2 makes a long calculation and returns 1 over 1024. So it returns 2 to the minus 10. M of 2.5 makes an even longer calculation. And at the end, it returns 2 to the minus 31. And M of 3 returns 2 to the minus 1.5 billion and something. So never mind what this algorithm does it even terminate for every input? It's not so clear, because if we want to prove it by induction, then the inner recursive call m of x minus 1 is okay, but then m of x minus 1 might return some very small number. So you make a recursive call of m of x minus a very small number. It's not clear that you get down to 0. So the answer is yes, this algorithm does terminate for every input, but it's not so easy to prove. In fact, Peano Arithmetic cannot prove that this algorithm terminates for every natural input. Now let's talk about a puzzle involving fuses. This is
so to prove it, you need transfinite induction up to what?
Up to epsilon 0.
Up to epsilon 0.
Yeah. Yeah. I'm going to explain the ordinals and yeah. So this is some famous puzzle involving fuses. So you have a bunch of fuses, each of which can burn for 1 hour, and you want to measure 45 minutes. So you cannot cut the fuses, and you cannot put marks on them or measure them because they don't burn uniformly. So the solution is as follows. You take two fuses, you light both ends of the first fuse simultaneously and one end of the second fuse. So the first fuse burns after 30 minutes, and then you light the second end of the second fuse. And so the second fuse burns for an additional 15 minutes, and that's how you get 45 minutes. So the question is, what other times can we measure this way? Suppose you have a finite collection of fuses that all of them burn for 1 hour, and the rules of the game are that you can light the fuse ends at the beginning, or at the moment another fuse completely burns, and at every instant in which you are allowed to light a fuse, you can light as many fuses as you like at the same instant. So this is called the set of fusible numbers, and you can define it mathematically this way. 0 is a fusible number, and whenever you have two previously constructed fusible numbers whose A and B, whose difference in absolute value is smaller than 1, then A plus B plus 1 divided by 2 is also fusible. Why A plus B plus 1 over 2? Because if you take a fuse and light one endpoint at time A and the second endpoint at time B, then the fuse burns completely at time A plus B plus 1 over 2. So we denote this operation A plus B plus 1 over 2 by A fuse B. Note that we didn't allow lighting a fuse only at one endpoint. We required lighting them always at both endpoints, but this entails no loss of generality, because if you want to measure one unit, you can do it this way by using two fuses. Okay, so this is the set of fusible numbers. So here you have a half and then 3/4. So here at 1, you have a limit point, and then this limit point gets sort of copied infinitely many times up to 1.5. So at 1.5, you have a sort of a double limit point, and then this double limit point gets copied over and over infinitely many times up to 1 3/4. So at 1 3/4, you have a triple limit point, and things get more and more complicated as you go to the right. Every fusible number is a dyadic rational, which means a fraction whose denominator is a power of 2. Okay, so there might be several ways of constructing a given fusible number. For example, here you have, so 5 over 4 is fusible, and here you have two different ways of constructing it. So we first prove that this set is well ordered, meaning that it doesn't contain infinite decreasing sequences. So the proof is as follows. Suppose for a contradiction that F, the set of fusible numbers, contains infinite decreasing sequences. Each infinite decreasing sequence has a limit, and there must exist a smallest limit, because the limit of limits is a limit. So let L be the smallest limit of an infinite decreasing sequence. So here you have it. Each purple bar is a fusible number that is constructed by two previous fusible numbers, xn and yn. Let's say that xn is smaller or equal to yn. And so you can assume without loss of generality that the sequence of x's is either increasing or decreasing or constant, because you can take a subsequence if necessary. But x cannot be decreasing, because since x is the smaller of the two, it has to be at least half smaller than L. So the sequence of x's will be an infinite decreasing sequence that has a smaller limit, which contradicts the minimality of L. So L has to be constant or increasing, and then y has to be decreasing in order for the z's to be decreasing. And if x is constant, then you see that the limit of the y's has to be smaller than L as well. I'm going to skip over the details, but you get into the same problem again. And if x is increasing, then things are even worse. So that's the proof by contradiction. So we know that this set is well ordered, meaning it has no infinite decreasing sequences. We can also prove that it's closed, meaning it contains all its limit points. I'm not going to go over the proof. So for example, you have a sequence of fusible numbers that converge to 1, and you also have 1. 1 itself is also fusible. So that always happens. You always contain all the limit points of the increasing infinite sequences. Okay, I'm not going to go over the proof. Okay, so I'm going to give some background on ordinals. So ordinals are a very central concept in mathematics. So first, there's the concept of well-ordered sets. So a set is well-ordered if every non-empty subset has a smallest element. Put another way, a set is well-ordered if it contains no infinite decreasing sequences. And so here I have two well-ordered sets, A and B. You see they have infinite increasing sequences, but not infinite decreasing sequences. So you can prove that for every two well-ordered sets, one of them is always isomorphic to an initial segment of the other. So here B is isomorphic to an initial segment of A. Okay, so put another way, for every two well-ordered sets, one is an extension of the other. So that means that well-orderings are themselves well-ordered by extension.
So it's just isomorphic, you mean?
Exactly, right. So why are these well-ordered sets important? Because they allow you to use transfinite induction. So for example, if you have a well-ordered set X and some property phi, and you want to prove that phi holds for all the elements of X, so if you can prove that whenever phi holds for all elements smaller than X, it also holds for X, for little x, that means it holds for all the elements in the set. This is called transfinite induction. There's a nice way of defining ordinals. So ordinals are for well-ordered sets are split into equivalence classes that have the same type. And so each type you call it an ordinal. But there's a neat way of defining ordinals in ZFC, in the Mellor-Frankel theories. You put sets inside sets, and you say that, and the relation is containment. I'm not going to, so here you have an example. So the empty set is the first ordinal, and then the set of just the first ordinal is the second ordinal. And so you get all the finite ordinals, and then omega, the first infinite ordinal, is just the set of all the previous ordinals. So each ordinal is the set of all the previous ordinals. It's a kind of weird way of defining ordinals because you put sets inside sets inside sets. It's kind of weird, but it's nice also. You can define operations on ordinals. For example, alpha plus beta is basically putting beta after alpha. And addition is not commutative. You have to be careful. Multiplication, alpha times beta, is you replace each element of beta by a copy of alpha. And this is also not commutative. You can also define exponentiation. There's also the operation of limits. If you have an infinite sequence of ordinals or any set of ordinals, you can define the smallest ordinal that is larger or equal to all of them. And in the von Neumann definition, that will be just taking the union. The limit is the union. Okay, there are two types of ordinals: successor ordinals, which have a largest element, and limit ordinals, which do not have a largest element. And there's also the zero ordinal, which is the empty ordinal. Then this famous ordinal epsilon zero, which is the limit of omega, omega to the omega, omega to the omega to the omega, and so on. And there's what's called Cantor normal form. Each ordinal smaller than epsilon.
Just a second, excuse me, Gabriel, maybe it was not very clear. Can you go back very briefly again to powers of ordinals?
I didn't define it. I skipped the definition. Yeah.
In fact.
Yeah.
In fact.
I'm not giving all the theory because I just have a limited time. But you can define it. You define exponentiation somehow, and then you can write each ordinal smaller than epsilon zero as an expression like this, with, like, for example, you have omega to the omega to omega times 5 plus, things like this. So it's some kind of recursive form of ordinals smaller than epsilon zero.
Excuse me. Alpha to power beta is just, maybe I'm just failing my exam completely, is just the set of maps from one to the other.
That have finite number. Fine.
I was sure I missed something in my answer here. Yes.
So yes, indeed. So
Ordinals.
Okay, there is indeed this slight issue. So that there are say nice graphical way of defining this exponentiation. So for addition multiplication, so basically this graphical definition. So one order to the right of the other, you put one order for exponentiation. So yeah, so basically the definition of half, but it's not, I guess, that intuitive. So the idea is there's the thing called transfinite recursion. So you basically could define the function iteratively on each next ordinal. So you use you define the function.
So function omega, for example, omega to power of such ordinal, you define inductively.
Yes, exactly. So you say that omega. So you suppose you already know what's omega to alpha.
But you can also do that. What he says, you can define alpha to the beta as a set of all functions from beta to alpha that map only finitely many elements to non-zero, something like that.
Yes, but then you need to specify
And then you have to specify the order, and you have to prove that it's a well order.
Yeah, okay, that's some way.
Yeah.
But you think that you define inductively, so let's say omega. Define it in a clear way.
Yeah. So if you already know what omega to alpha is, then omega to alpha plus one. What is omega
times omega?
Yeah, you just multiply by omega,
and then taking limit is taking limit.
Yes, and it's continuous. So
Right.
on limit ordinals, you just take this limit.
And it doesn't have to be omega. It can be any base.
Yeah, and this of course so you need to determine the function. So you could prove this basically by transferring the induction ordinals.
Yes, and it should be also provable by induction that the two definitions
Are equivalent. Yeah, and also addition, multiplication, you can define it by transferring induction.
in the same way.
Yeah. So each operation has two definitions.
So again, so alpha and beta are maps from beta to alpha such that they're zero except at finitely many positions.
Right. Yeah.
Right.
Yeah. If I remember correctly, that's the definition.
Right.
Yeah.
Perfect. Excuse me.
Yeah. Okay. So.
And by the way, again, please excuse me. Counter normal form theorem is quite non-trivial.
No, it's easy. It's easy.
Yes. So basically, you prove it by no. Okay. Yeah. So basically, okay. No. You don't. Yeah, you prove it by transferring induction. So the point is that first you find the greatest alpha one such that your ordinal alpha is less than equal to omega alpha.
Sure.
And then basically you.
And you look at what's left.
You find the smallest ordinal such that when you add to the right.
Yes.
Okay.
So on and so forth.
Probably it's unique. Right?
And it's unique.
All right. It's unique.
Yeah, it's unique. Yeah.
And it's why is it unique? It's sort of clear.
Yeah. Yes. And so yes. And then the point that this ordinal will be smaller than alpha. And because of this, you could use transference induction assumption.
Right.
That there exists counter normal form. And then use the counter normal form of what's left.
Right. Okay.
Yeah. Okay. So then, we prove that the order type of the fusible numbers is epsilon 0. Okay. So we know the fusible numbers is a well-ordered set, so it must have an order type. So we just proved we gave an easy proof that it's well-ordered. So okay, it has to have an order type. We have absolutely no clue what the order type is. So you have to work harder in order to prove that the order type is in fact epsilon 0. So the proof is in two parts: a lower bound and an upper bound. So here's the proof of the lower bound. We prove that there is a subset of fusible numbers whose order type is exactly epsilon 0. And this we call tame fusible numbers. And you construct the tame fusible numbers by transfinite induction. So you construct them first up to 1. So you see in the screen the tame fusible numbers up to 1. You see they have a limit at 1. And then let's go this. Okay, let's suppose that you already defined them up to x plus 1, and you want to keep going. So you go distance 1 left to x, and then you go right to the next tame fusible number that you constructed, which is y. And now I'm going to show you how to define the tame fusible numbers up to y plus 1. Okay? So you measure this distance between x and y, let's call it m. From x plus 1, you go distance m left, and you do this thing. You take the fusible number y, and you fuse it with all the fusible numbers in the first interval, and you get fusible numbers in the second interval. And then again, you apply y to the second interval, you get a third interval, and you repeat it infinitely many times, and this thing converges to y plus 1. Okay, so this this argument show that if you define it up to x plus 1, you can go on to a y plus 1. Now imagine that after y, there's another fusible number, but closer together, and then you still have an infinite sequence that converges to something. So you have to apply this argument infinitely many times to get to that limit plus 1. Okay, so after you did it infinitely many times, you keep going. Okay, so it can sound of weird, but mathematically it's okay. That's how transfinite induction works. Okay, so now let's look at the order type of these tame fusible numbers. So we prove by transfinite induction that if the order type up to x is alpha, some ordinal alpha, then the order type up to x plus 1 is omega to the alpha. Okay, so we'll do it by transfinite induction. Suppose it is true for x.
I should say, maybe it sounds, for me, it was, I should say, for me, it was very surprising that what you do is like x plus y plus it's 1 over 2, right? It's contracting semigroup. It's contracting, it's most obvious contracting semigroup. So just, and the ordinal, you get omega to power. It's sort of, once you hear Gabriel, this is your observation.
Well,
This fact is what you're exposing. This is observation by yourself.
no, I think the epsilon 0.
Yes.
No, there was already.
Tame and so on.
No, already Jeff Erickson pointed out epsilon 0. He just didn't realize that not all fusible numbers are tame.
Ah, okay. So it's Erickson's observation.
Yeah.
So you'll see it's two-line proof. But just the very fact that you get so many so quickly that this simple operation actually somehow results in this big increase in ordinal type. This to me was very surprising.
Yeah. So suppose that the order type up to x is alpha, and that the order type up to x plus 1 is omega to the alpha, and so the order type up to y, so y is in the next guy after x, so its order type is alpha plus 1, and we want to prove that the order type up to y plus 1 is omega to the alpha plus 1. Okay, so why is this so? Because here in the purple segment, the first purple segment, you have an ordinal which is a final segment of omega to the alpha, so it itself is omega to the alpha. Okay, so sometimes if you have an ordinal and you cut it and take the right part, you get the same ordinal. Okay, and so you take omega to the alpha and copy it omega times, so you get omega to the alpha times omega, which is exactly omega to the alpha plus 1. Okay, then you have to argue by a limit argument about limit ordinals, and everything is okay. So the conclusion is that the tame fusible numbers, the order type is what you see here. You have a tower of omegas. So therefore, its order type, when you look at the whole real line, is epsilon 0. Then there's also this thing about, okay, so not all fusible numbers are tame. So this is the smallest non-tame fusible number that we know of. Now regarding the algorithm M, so suppose you are given a real number R, and you want to find the distance between R and the next tame fusible number that comes after R. What will you do? So according to the definition of tame fusible numbers, you have to do the following. You have to go distance 1 left, look at the next tame fusible number, y, measure that distance, then go left that distance from R, and okay, I'm going to skip the details, and basically what you get is this. So now we know what this algorithm does. It gives the distance to the next tame fusible number. Okay, there's the question of the rate of growth of this function. So this function, as you saw.
So you also skipped the part why the set of all fusible numbers is not bigger than epsilon 0.
No, I didn't get to it yet. Maybe I should skip it actually.
Oh, no, it's not okay.
But I didn't get to it.
But this question is sort of remains on the margin.
Yeah.
Right.
Yeah.
Excuse me.
Maybe I get to it. Okay, but first let's talk about this function m. So as r grows to infinity, m of r grows to 0 very quickly, meaning 1 over m of r grows to infinity very quickly. The question is how quickly. And so for this, we have to talk about fast-growing functions. So maybe you once heard about the Ackermann function, which is a very fast-growing function.
I'm really unconvinced. Pierre, have you studied Ackermann function?
So if not, then
it's like something super.
Maybe. Yeah. So it's like this. So the first function you define a1 of n as 2n, then a2 of n is given n. You apply the previous function n times, starting with 1. So you get 2 to the n. Then the third function is you apply the second function n times. So given n, you get 2 to the 2 to the 2 of height n. And a4, a5, and so on. And then to get the Ackermann function, you take this two-dimensional table and you sort of columnize. You take the third column, for example. Okay, so you get a function that grows faster than ak of n for every finite k. Okay, so that's Ackermann's function. Now you can say, well, we can continue this. Let's take Ackermann's function and apply it n given n. Apply Ackermann's function n times, and you get some function b. And then you can do the same with the function b and get some function c. Okay, and then you can columnize once you do this. Okay, then you guys sort of confused how exactly you do this. So that's how ordinals come in. So for every ordinal smaller than epsilon 0, you can define a sequence of ordinals that converges to that ordinal. Basically, you take the rightmost omega and replace it by n. Okay, I'm going to skip the details. But basically, what you do is if you want to define f alpha of n, well, alpha is some ordinal. So for each ordinal alpha, you have a fast-growing function. So how does it work? F alpha of n, you take this sequence that converges to alpha and take the nth element of that sequence, and you plug in, let's say, 3. And so Ackermann's function is just f omega of n. Actually, you do it a little differently. Okay, so basically what you get is that for every ordinal alpha, you have a fast-growing function f alpha of n, such that whenever alpha is larger than beta, f alpha overtakes f beta. And it also overtakes any finite number of compositions of f beta. And then you sort of columnize one final time, and you get f epsilon 0 of n. So this final function is called, has the index epsilon 0. So this function 1 over m of n grows like f epsilon 0 of n. That's how fast it grows. So I'm going to skip the proof. This is the upper bound. As Sasha said, you also have to prove that the order type is not more than epsilon 0. If we want to stop at 3, I think we should skip it. There's more.
Leave it as exercise.
Yeah, this is the exercise.
It's also in the survey, which, by the way, is very well written survey that
Yeah. Basically, if you want to build this some ordinal z here between these two black bars, you cannot use an ordinal in the same interval. You have to use ordinals in the previous intervals. That's how you get to bound this thing. But let's talk about Peano Arithmetic. First, there's first-order arithmetic. It's a language that you can use it to say things about the natural numbers. So you have quantifiers existent for all. You have variables, and you have 0 and the successor function. And addition and multiplication, and equality and logical operators. So you can say, for example, so you can construct the natural numbers this way with a successor function, and you can say, for example, for every x there exists a y such that x plus 2 equals y. Okay, so each thing you say can be either true or false. For example, the second one is false. So each equation, each formula has free and bound variables. You can define, for example, mod, like a remainder. You can write a formula that says that x is prime. You can, for example, write a formula that says that the prime numbers contain arbitrarily long arithmetic progressions, or things like Goldbach's conjecture that every even integer can be written as the sum of two primes. You can talk about natural numbers. The question is, how do you talk about sequences of natural numbers, finite sequences? So Gödel found a way to do it using the Chinese remainder theorem. I'm not going to go into the details, but suppose you want to talk about you have a finite sequence. So Gödel finds a way of encoding that finite sequence of any finite length into a triple of natural numbers. And you can talk about the ith element of the sequence. And once you have finite sequences, you can, for example, talk about exponentiation or factorials, Fibonacci numbers. You can talk about finite structures, trees, graphs. You can define rational numbers, algebraic numbers. You can talk about Turing machines. So you can do many things in Peano arithmetic. There are some things you cannot do in Peano arithmetic. You cannot quantify over all the reals or over all infinite sequences or over all infinite sets, because these are uncountably many. For that, you need second order arithmetic. Okay, but for example, you can talk about fusible numbers in Peano arithmetic. You can write a formula that says that the rational number z is fusible. You can say algorithm M on rational input R terminates outputting rational number Y. And the Peano arithmetic is a set of axioms and rules of inference for first order arithmetic. And as Gödel proved, any axiomatic system strong enough to model basic arithmetic contains sentences that are true but cannot be proven unless the system itself is inconsistent. So in particular, Peano arithmetic has things that are true but cannot be proven in it. So Gödel constructed a complicated sentence G that is true but cannot be proven, and people started wondering were there natural theorems that cannot be proven in Peano arithmetic. So Gensen was the first to make some progress here. Then came the famous Paris-Harrington theorem, which talk about coloring k-tuples of natural numbers, and it has to do with the Ramsey's theorem, in the infinite Ramsey theorem. Then came a few other things, good stain sequences. Hydras, it came of hydras, where Hercules chops a head of the hydra, and then the hydra sprouts new heads, and then Hercules chops again, and somehow the hydra always dies, though it doesn't seem so obvious. There are a few other things, and there's this general technique for proving things that Peano arithmetic cannot prove something. So suppose you have a Turing machine that terminates on every input. So given a natural number, the Turing machine constructs another natural number and terminates. So the Turing machine basically computes a function, g, from naturals to naturals. And suppose that Peano arithmetic can prove that this machine terminates on every input. Then this function g that the machine computes cannot grow too fast. its rate of growth must be bounded by f alpha of n for some ordinal alpha smaller than epsilon 0.
Wait, what is f alpha? F is what we defined before.
F is a fast-growing hierarchy.
Which one?
The fast-growing hierarchy, these fast-growing functions that go beyond Ackermann's function.
Right. So these ones, A, B, C, and so on.
Yeah,
Right.
yeah.
ABC, so
ABC was the bad idea.
Omega times 2.
Right. No, right. And we continue. No.
Yeah.
This is, no.
Yeah. So basically, what this says is that if you have something that has a rate of growth f epsilon 0, then Peano arithmetic cannot prove something over there. Okay? So this is a general technique for proving that things are unprovable in Peano arithmetic, and with this tool, you can prove the Paris-Harrington and the hydras, everything you can prove with this. Okay, all they have the same technique, and no, with this.
No, I mean, it's I guess okay. So you actually you could your second
Could not.
But
Goddard uses a different technique that is.
No, that is clear. But I mean, is it whether it's possible to reach it?
okay, so basically
No, but this is specific to Peano arithmetic. Goddard makes something for any system.
No, I agree, but the question is whether it's possible to prove the specific.
and so there is important.
I don't have any rate of growth. I don't know. Just
Right.
So basically, the sample is called PA. It doesn't have a rate of growth. So it's it's not, basically when you say called PA, you don't say that some Podgram function is total. But basically, you slightly modify code PA. You rather say that if they prove statements of this form that some Turing machine terminates, then the statement is true. So this is called one reflection, and basically then this is the basically you so this consistency, so sigma one reflection. Okay, it actually you could regard to this kind of Pascal function, and actually essentially it corresponds to this function epsilon 0. And I essentially one basically should look whether say whether you get to the circular argument, so whether basically when we could in some way use secondary completeness. But probably they don't. But this I am not completely.
Okay. No, that makes sense.
Yeah, but yes, but probably but basically you could do.
Yeah. So here, regarding fusible numbers, he has some second-order statements and some first-order statements. So second-order statement, F is well-ordered. This is a statement that talks about infinite sequences, so you cannot formalize this statement in Peano arithmetic. And algorithm M terminates on all real inputs, so this statement quantifies over real numbers, so it's a second-order statement. But on the right, you have first-order statements. The first one says that for every natural or rational number, there exists a smallest fusible number larger than it. And this you can formulate in Peano arithmetic. Algorithm M terminates on all rational inputs you can formulate in Peano arithmetic. Every fusible number has a maximum height representation. You can also formulate it. So all these first-order statements are unprovable in Peano arithmetic. Okay? And the proof is like this. So these are the three statements. So we already know regarding number 2, we know it's unprovable because the rate of growth of M it grows like epsilon 0. Then from 2 you can derive 1, and then from 1 you can derive 3. I'm not going to go into the details. That's basically it. I also prepared a small presentation regarding our new work. We have 5 minutes. In 5 minutes, I have to figure out how to switch here. Here it is. Okay, so this joint work with Fedor and Sasha. And okay, so first, some quick introduction to large countable ordinals.
It's not on the. No, we should.
What should I do? I should. she said I have to upload. How do you switch screens here? With the here in the plus.
No, it should be on this.
How do you switch screens here?
How do you, where is this? So,
Yeah, here plus.
So this is the old one, right?
Yeah. So yeah. Stop this plus upload confirm. Right?
Right?
Yeah.
Yeah.
And then what do I do? Then
And then you return back to your presentation.
here. No.
This new one.
Where is it? How do I find it? Here. I don't know what do I do exactly. Okay, so here. Okay, so let's do like this.
Alyosha, can you see now the new presentation? Alyosha.
Да, что?
Видишь новую?
Да.
Okay, so they say it in Moscow.
Okay.
The presentation.
So you can show it here. Is it big enough?
It's small. You need to turn on. That's fine for them, but you need to turn on this window and make it big.
Full screen. But then does it switch over there? I'm not sure it switches over there. No, over there it stays the same. It's not. Does I do like this and that's
Okay,
it.
yeah.
Okay, that's fine.
Okay.
No, I think we just
Oh, you can switch slides
on the
Ah, here.
Just go to the presentation mode.
Okay. Okay, so you can go beyond epsilon 0. You can take like epsilon 0 plus 1 and put it on top of a tower of omegas, and you get this ordinal called epsilon 1. And you get epsilon 2, epsilon 3. You can get to epsilon, epsilon 0, epsilon, epsilon, epsilon 0. And that limit is called phi 2 of 0. And then you can do phi 3 of 0, phi 4 of 0. You can do phi 5 of 0 of 0. And then phi 5 of 0 of 0 of 0. And so on. You get its ordinal called gamma 0, which is called the Pfefferman-Schutte ordinal. But you can go on and so instead of writing, what did I do?
Excuse me, here, yes, exactly.
Here.
It's a small ordinal, so you need to make it smaller.
Okay. So you can write phi with finitely many inputs. So the Pfefferman-Schutte ordinal is actually phi 1, 0, 0. And you can put more zeros and take the limit, and you get what's called the smaller Veblen ordinal. There's also a large Veblen ordinal. Okay, so we want to generalize the fusible numbers. So you take a function from n tuples to reals that is monotone, meaning that if you increase the inputs, then the output increases. And you take some initial element, and you construct a set of elements like we did with the fusible numbers. And you can prove that this thing will always be well-ordered. And the proof, it looks at trees, because each element that you construct is basically a tree. And if a tree embeds in another tree, then the first number has to be smaller or equal to the second. And then you apply Kruskal's tree theorem, which says that in every infinite sequence of trees, there is always a tree that embeds into a later tree. And since for Kruskal's theorem, you have this small Veblen ordinal, that's the upper bound for.
And by the way, it's also unprovable not only in Peano Arithmetic.
So basically, the solving epsilon 0 is a function of Peano Arithmetic, but indeed the several natural theories that that have importance below small W0.
And so then the question was whether actually with ordinals you can get, okay, so you can also use several functions or initial elements to get things a little higher. But anyway, the question was whether there's a natural function f that using this technique gives you some big ordinal for the set G. For example, this function, which is a natural generalization of the fusible function. And that's what, for example, Friedman asked. And the answer is no. So we proved that, first of all, with this function, this natural generalization of the fusible function, you get to phi n minus 1 of 0, okay, which is very low, it's very disappointing. It's not even gamma 0. And then we proved that for any linear function, you cannot get more than phi n minus 1 of 0. So how do you get these huge, amazing ordinals? We don't know. Okay, but that's it. Thank you very much. What?
Can we get higher ordinals? Can we get
Yeah,
higher,
because the proof that is based on the trees is an upper bound, but the question is whether that upper bound is tight or not. Yeah.
So somehow, can we get, so we have this simple separation, x plus y plus 1 over 2. We get, well, we get to some ordinal. Can we do, so, okay, how far can we possibly go? How far can we go comes from Kruskal theorem, which gives this very small Veblen ordinal, which is much bigger than upper bound, right? Which is an upper bound. So, so there is a very big gap between lower and upper. So we say, but is it possible to somehow bridge this gap using more functions, more? So no. So the answer is no.
At least with linear functions, no, and
so no, we cannot do better than. So it's all like there is nothing. At least this is the result. There is nothing better.
No, but it's just for linear functions. So
Okay.
You know that there exist quite weird functions that actually use this plateauism, but
not functions of arithmetic.
not nice functions.
Yeah, that's really weird.
Not functions of arithmetic nature, which is the whole point.
Right. Okay. Questions?
Thank you very much.
Thank you.
Next time we ask you for a mini calls.
Okay.
Questions?
I asked previous naive question, straightforward. So in your very first recursive formula, what happens or what can possibly?
Which recursive formula?
For feasible number.
That's the answer is on the blackboard.
No.
Maybe I didn't understand the question.
The algorithm M?
So yeah.
Well, let me.
I didn't understand the question.
Yeah, I didn't understand the question. Let's go to the first slide.
Let's see.
Yeah, just
How do I?
If you consider functions of several arguments, then nothing happens, which is exactly the result. Maybe I'm not sure.
I mean,
Maybe you mean
it's a
something else.
recursive formula.
A recursive formula for M.
Yes, for M.
Ah, okay. So the algorithm at the beginning, right?
Yeah,
This was Fedor's question with which we started, but I think we don't have any.
No, we actually, okay, we actually, I think, I'm not sure. Say, but yeah, I think it will be what happens with some very natural generalization.
This formula?
Yeah.
Yeah. So up to 3 to get this.
No. The question is, what is the formula if you try to define other type of feasible numbers? Denominator of 3 instead of 2 or.
Ah, okay. I see. Yes, I didn't look at it so much, but I think
This doesn't change anything. I mean, not bigger.
But basically, so what you could true is yes, of course. Okay, so
Surely, Gabriel, in Israel, you're used to Russian. In
Yeah,
Tel
yeah,
Aviv
we
University,
have-
you're used to Russian style sandwich.
chalk or
We have chalk, yes. We have chalk.
Oh, yes.
But if you just put something like 3, nothing.
No,
I mean,
if you put,
it doesn't-
I don't know, but
But it
should-
doesn't
shouldn't-
become
it
better.
shouldn't- Yeah, I mean, it shouldn't. Yeah, but basically, I think so. This, I remember correctly. Basically, if you look on this kind of function, and of x is again minus x if smaller than 0, and here is a trick. So instead, we do something like this: mn of x minus mn of x minus and so on, mn of x minus 1
Divided by n, I guess.
yeah, exactly, yeah, divided by n. Otherwise, yeah. Otherwise, and of course, here we have n instances. Yeah, and the point, so our original function will be m2. And the point is that basically, as far as and so if I remember this correctly, so okay, let's call this a conjecture. I think actually because I will show this the case. So basically, this mn, the function mn corresponds to the analogues of tame fusible numbers, but for functions x1, as example, plus 1.
So exactly nothing new.
Yes,
So nothing new. Which is
No, okay, yeah, but it's but basically you get slightly larger order. So you get m2 with m2 you got epsilon 0, and here you get phi n of
Phi n minus 1.
phi n minus 1. Yeah.
Yeah.
So you
Yes.
go up the blend higher.
Yes. But basically, yeah. So we have the analogy here, yeah. But no. But so perhaps if you do something more interesting with this, because we could get something much more complicated. But this I don't.
You don't have such example. Well, this is my question. So, why who did come up with this formula for m because it's not easy to see what this formula is for? Why it should give something? No, but it's because of Fusible. This is what we were saying at the beginning. So it's exactly first. What was first, like fusible numbers or some formula?
First, the fusible numbers. Jeff thought that that formula gives the distance to the next fusible number, but he didn't realize that the tame fusible numbers are not all the fusible. He thought all fusible numbers are tame. So he figured out that formula.
Okay.
Yeah.
But fusible numbers came first, right?
Right, fusible numbers came first. Yeah.
Fusible numbers are the more. But this question makes a lot of sense. So if you write some such recurrent definition, more complex.
Yeah, that's exactly what Friedman wanted. He wanted to build these general fusible numbers and get some algorithm that's cute like the algorithm M, and that you cannot prove that it terminates in some stronger system. That's the motivation. Okay.
Moscow, Alyosha.
What about the set of the physical numbers is when n is equal to 2?
Yeah.
But what about is there any connection? What about if we consider n equals 3? Is there, for example?
No, n equals 3, you get phi 2 of 0. You get, yeah.
Bigger, but not very much bigger.
You get phi n minus 1 of 0. You get a bigger ordinal as n increases. Okay. Yeah.
А Москва нас слышит, Леш?
as a microphone is for
Maybe
okay.
okay.
Okay. So maybe you should ask them, Moscow people, if they have.
Do you have a question in Moscow? Hello.
Questions they tell us. Okay.
So somebody's typing this.
Ah. Typing.
Yeah, it was written like typing. So. Open the browser in the chat. Oh, somebody's typing in the chat.
How do you open the
okay.
chat? Public chat here.
We should. No. No questions, thank you. Okay.
Okay, thank you.
Okay. Yes. No. But you had a question.
Just maybe like a question. Maybe if you know, either so you have direct connection from this of fusible numbers to this recursive formula to the ordinal. So is there any connection? Just curious of fusible numbers to some very classical number theory or something like this.
I don't know.
Yeah,
Just
what,
maybe
like
if
what?
You know, just
Like
curious.
what? Connection of what type? Question. Maybe I'm not sure.
Oh, well, different. I don't know. Analytic number. So do they appear in some number theory, or this is the constructions that you like more or less?
I think I wouldn't say something like analytic number theory. Hey, haven't been working on this, so maybe that. But I think it was I think both Jeff and Gian, they are so they have computer science background, right?
Yeah.
Yeah. So yes. So this is.
Maybe it's not clear what connection question.
No, I don't have it in mind. This is questionable. There are some other use this feasible.
There seems to be some sort of natural dynamical system.
Okay, thank you.